Yeah, so the geometric series, do we remember what the sum of that is? Remember that is a over 1 minus r. Provided, of course, that something has to be true about that r, right? Provided, of course, that the r, absolute value of r, is less than 1. Okay? All right, so how are we going to use that to figure out to change certain functions into power series? Well, what we do is this is still valid for a variable as well. This also works for a variable. So in other words, we could say the geometric series with r as a variable, in other words, an x instead of an r, we can just use this exact same formula. It's still valid, provided, of course, that this x is less than 1, absolute value x is less than 1. Okay, so the first one that we're going to see is, or at least to see how this kind of works, really what we're going to do here is we're going to be trying to look at a function that starts out there, and we're going to go the other direction on that and change it into a power series. In other words, we're starting now with the right-hand side of that geometric series formula, and we're going to change it into the left side. Okay. So notice the first thing we can do here, the first other power series we can generate from that is this. Notice that if I have a plus instead of a minus there, like if I put a over 1 plus x instead of a over 1 minus x, then I can rewrite this as 1 minus negative x. See? And then the way that we approach this is we say, okay, whatever is in the parentheses right here is going to take the place of the x right there in our power series. And this is actually the operations with power series at the top there, that operation number 1, operation number 1. That says if you have a composition of two functions, and the composition here being negative x composed with this a over 1 minus a over 1 plus x, sorry, a over 1 minus x. What that's saying is that we can just replace, again, the x in the power series with the negative x. So what we're going to get when we do that is this. The a stays, but instead of an x, I put a negative x. And then I can rewrite that as negative 1 to the n x to the n. But that's what this is saying then, is if you have a over 1 plus x, you can change it into this power series right here. Okay? And if you have a over 1 minus x, then you can change it into this power series right here. Okay? So that's the idea here. We're going to make use of both of these, a over 1 plus x and a over 1 minus x. I'll just note that here. We're going to make heavy use of both of these. And then, of course, both of these are for, these would only converge if x is less than 1. Okay. All right, so how are we going to do this? So let's take a look at that first example. So the goal here is, again, to find a power series representation for this function, 2 over 5 minus x. How are we going to make use of, in this case, it'll be the first of those two that I just wrote up there, a over 1 minus x. This looks almost like that, except what we need to do to make use of this is we have to make it match exactly. In other words, I need to see a 1 right there. There has to be a 1 right there to make use of that. And there has to be a negative right here to use this one. Okay, if it was a positive, I would be using this one. So I want this to be a 1. In other words, that needs to be a 1. How do I make it be a 1? Well, I can just factor a 5 out of it. That's the easiest way to do it. Just factor a 5 out. When I factor a 5, I'm left with 1 minus, and then when I take a 5 away, I have to have that x over 5 there. Okay, and then you can write this, if you want to, as 2/5 over 1 minus x over 5. And then if you think about, what I did on that example here to change this, right? What did I do? I replaced that quantity there into the power series, right? Wherever that x was, I replaced it with that negative x. So we're going to do the same thing here. We're going to take this quantity here, x over 5, and it's going to replace that x right there. This is the composition thing. That's the first thing on the operations with power series at the top of the page. That's how we use that, okay? And so what we can do then is say, well, this must be the power series, n equals 0 to infinity. A, in this case, is 2/5, so I'll just put the 2/5 there. And then I have, what, x over 5. Right? X over 5 to the power of n. And this, now, for convergence here, it's the same thing. Whatever this quantity is, that's the quantity when we were looking up at the other one that had to be less than 1. So that is also telling us that that quantity has to be less than 1. Okay, and then you can simplify that and say absolute value of x must be less than 5. So it turns out that this quantity here, when you do that, that is in fact the radius of convergence for this power series representation of that function there. Okay, so this thing is only going to converge between minus 5 and 5. 5 units away from the center being 0. All right, now one other thing just to point out here, and this is not 100% necessary, it's just kind of makes it look a little nicer. Notice that we could rewrite this as 2x to the n over 5 to the n plus 1. Why is that? Because again, that's a 5 to the first power. This 5 has the n power applied to it, so that's actually 5 to the n. 5 times 5 to the first, well, that's 5 to the n plus 1. Okay, so what we have is like a nice cleaned up version of this power series. It's only going to converge 5 units away from the center, though. So what do we take away from this? We take away that if I were to graph this function on my calculator, look at it, we kind of know what that function is going to look like. It's a reciprocal function, maybe shifted 5 units to the right and flipped over, and it's got a graph, right? It's got a vertical asymptote at 5. You graph it, and then you were to also graph this power series here, what do you think you'd see? Well, according to what we've just been doing, you should see exactly the same thing. The function and the power series, there's no difference between the two of them. They produce the exact same graph. However, this function we know has a domain that goes on forever except for 5. 5 is the only number that's not in the domain, but every other number is. So if you graph that thing, it's going to look like that function forever, right? But if you graph this thing, it's going to match that function, but where? Only between -5 and 5. After you get away from, 5 units away from the center, what's it going to do? Well, then it's going to start shooting off to infinity like that other graph that we saw, or shooting off to negative infinity. So it will match the function exactly, but only on that interval from -5 to 5.
I always like comparing these functions, comparing the original function, graphing it, and then doing a partial sum or a partial sequence on those and plotting them together and see how you add more terms, how the convergence gets better and better. It's very interesting.
Yeah, let's do that. In fact, I think that's a good idea. Let's go ahead and do that because it's a good idea. So I'm going to go ahead and show you the graph of the function and the power series at the same time. So the power series that we got was 2x to the n over 5 to the n plus 1. Okay, so there's the power series, and I have it, let's move it down to just 2 for now. And then let's also go ahead and graph the original function. Y equals 2 over 5 minus x. Okay, let's take a look at this. So the thing in green is the function, right? And the thing in red is the power series representation of the function. Again, right now I have that slider set at 2, so this is only a second degree polynomial. It doesn't really match it very closely. But watch what happens when I increase the power, or the upper bound on that summation. It seems that I'm getting more and higher degree polynomials, right? This is like a 12th degree, 13th degree, 14th. What happens as I keep increasing those degrees? Let's take it all the way to 100th degree, and you can see, well, once the computer figures it out, look how closely that matches, and look where the matching ends, right? Look where it stops matching. The computer's still thinking about it, I think. See that? You can't even tell the difference between the green and the red, right? They're almost identical. So they match very closely. But look where the matching ends. Look where it stops matching. Particularly over here, right? Look at that. -5, right? That's 5 units away from the center. And that was where the interval of convergence ends, right? 5 units away. And so that's why the function stops matching, or the power series stops matching the function at -5. Any value beyond that, it's going to diverge, meaning it's going to shoot off to infinity, or to negative infinity, perhaps. okay, this thing is centered at 0, but suppose I wanted it to be centered somewhere else, like not at 0. How could I do that? Could I center this power series at some number that isn't 0? And turns out you can. Now, the fact that this thing has a vertical asymptote at x equals 5, that's a pretty big indicator about what's going to happen with that interval of convergence. If I were to center this power series at, say, 2 instead of 5, right? So suppose I centered it at 2. That would mean that the interval of convergence is going to change because it cannot converge past that asymptote, right? And if I move the center over to 2, then I've gotten closer to that asymptote. I'm in fact only 3 units away from the asymptote there. And so what I would find is if I wanted it to be centered at 2, then my interval of convergence would actually shrink. My radius of convergence would shrink too, because I'm closer to that asymptote. What if I wanted to center it at like -2? Well, then I'd have a bigger interval of convergence because I'm farther away from that asymptote. Okay, so let me just show you real quick how you would maybe make this centered at a different value. So right now this thing is centered at 0 because, again, when you have a power series, if you look at this term right here, that is the value 0 is the thing that's going to make that whole thing 0, right? And so that's the center. Suppose I wanted it to be centered at 2. Let's say 2 instead. Then instead of having an x right there, what I would want to see there is an x minus 2, right? Because if I see x minus 2 there, then when I plug in 2, I would get 0, and then everything would be 0. So I want this to be centered at x equals 2. If it's centered at x equals 2, then I have to do these first steps a little bit differently. So this is what we started with, right? 2 over 5 minus x. I still do want that to be a 1, but I want this to be x minus 2 instead of just x, okay? So how do I do that? Well, I just say that I want it to be x minus 2. So what I'm going to do is say, I'm going to make it be x minus 2. But I can't just make it x minus 2. I have to also add 2. So basically, I'm just adding 0 in a clever way there. See? Maybe you agree that is the same exact thing. All I've done is subtracted 2 and added 2 from inside the parentheses, right? Then I can split that up and say, okay, I can make this 5 minus x minus 2 plus 2, and then I can take that negative and distribute it to both of those. Okay, that's the next way to think of this. So I'll do that here. So if I do that, I get 5 minus x minus 2, and then I distribute that 2, I get another minus 2, right? And then I can rewrite this as 2 over, well, now I've got a couple constants here, 5 minus 2, right? 5 minus 2, which is 3. So you put the 3 there. So 5, that becomes 3 minus x minus 2, okay? Now I'm at the point where I want that to be a 1, and so I factor a 3 out of that denominator. So I take a 3 away, and I'm left with 1 minus x minus 2 over 3. And then I can rewrite this as 2/3 over 1 minus x minus 2 over 3. Now this is exactly what I want. Exactly what I want, because now it is exactly in that form that I need it to be. So what we're going to get out of this is sum. I'll put the 2/3 here, so 2/3. And then I'm going to replace the x with x minus 2 over 3 to the n. And then we can also say that this is only going to converge provided that x minus 2 over 3 is less than 1, or x minus 2 is less than 3. And then if you want the interval of convergence, should be absolute value there, you could say minus 3, and then you could add everything, and you could say minus 1 to 5. This is only going to converge 3 units away from the center, right? As I said earlier, right? If we move that thing closer to the asymptote, it's not going to converge for as many values as x as it did before. And then if you want to, the last step here would be, you could say this is to clean it up a little bit. You could say 2x minus 2 to the n over 3 to the n plus 1. converging for all values of x between -1 and 5. Now, you might be thinking about the endpoints on these. Well, remember that this convergence is actually coming from the convergence of a geometric series, and the geometric series, that is a strict inequality, strictly less than, will never include an equality there. So in this way, you don't have to bother checking endpoints, is what I'm saying here. This is coming directly from a geometric series. Again, geometric series has a very set condition for convergence. That thing, that r, has to be strictly less than 1, not less than or equal to 1. All right, so now let me just show you, how did this change what we were doing before? Let me just show you on the graph how this is going to look slightly different. Okay, so we had a 3 up there, right? X minus 2n. Wait, it wasn't a 3, was it? What was in the numerator there? 2. 3 in the denominator. Well, look at that. Look at how it's graphing now. See, it's the same graph. I mean, it still matches it, but it seems like things have shifted over, right? It seems like now it's converging, kind of centered right there at 2 is exactly what I wanted it to do, right? And then look, if we increase this, look where it's starting to not converge, right? At -1. The interval of convergence is now smaller because we're closer to that asymptote, right? It can't converge past the asymptote, and it has to converge the same distance in one direction as it does the other. So therefore, it's only converging 3 away from the center now. The center now is 2, though, right? The center is here instead of at 0. Everybody see what's going on there? So my point here is that you can force these to be centered anywhere that you want. You can center them anywhere, except, of course, at a place where it's not defined at all. Like, you couldn't center this at 5 because it's not even defined there. But you could center it somewhere on the other side of the asymptote, right? I mean, the graph continues over here. So suppose you wanted to center it at 8. If you did, then the power series would match this part of the graph instead of the part on the other side of the asymptote. All right, you guys see how that works? All right, next thing on 11.9 deals with differentiating and integrating power series. So you can do both. You can take a derivative of a power series, as we've already seen, right, with that last example on 11. You can take a derivative of a power series. You can integrate a power series as well. And they're pretty, again, part of the reason why power series are nice is because it's pretty easy to take their derivatives. They are, after all, just polynomials. Polynomials are very easy to take derivatives of. So let me show you how this works. All right, so the goal here is still to figure out power series representations of functions. We still want to do that. So take a look at this second example. And the goal here on part A is to find a power series representation for 2 over x plus 1 cubed. Okay, now, so again, we're going to be using, in this case, we're going to use that second one of those where you have a over 1 plus x is equal to this power series. It says that we're supposed to do that, right? Right above the problem. Okay, now, again, the goal is to try to make it look as much as possible like that. A number divided by 1 plus x to the first power. Well, we have a problem here because that's not a first power, that's a third power. So how are we going to use that power series if we have a third power there instead of a first power? What do? This is where taking derivatives and antiderivatives comes into play, okay? What we want to realize is that we can rewrite this function. Let's rewrite it as, now if I want to get it so that that does have a first power, thinking about a way I might do that. Well, taking a derivative is not going to work, because if I take a derivative, I'll take that minus 3 and put it in front, and then that's going to lower down to the minus 4th power, right? However, an antiderivative will at least get us closer. So just notice what happens when I integrate this function. Well, if I integrate it, I have to raise that power by 1, right? So I'll get a -2, and then I'll put the negative in front of it. You guys agree? I didn't have to do any substitution there, because if I let u be x plus 1, then du is simply dx, so there's no problem with the dx there. So There we go. Now I'm at the negative 2 power. Let's do one more antiderivative here. If I do one more antiderivative, what am I going to get? Well, now I'm going to raise it to the negative 1 power, and I'll divide by negative 1, so I'll get x plus 1 to the minus 1 power. And notice that that is, in fact, let's write it like this, 1 over 1 plus x, right? And that is exactly this, right? That's exactly the same. And so we know what that is as a power series, right? 1 over 1 plus x is equal to this, okay? So notice what this is. This is the power series representation of the integral, I guess, second integral? I don't know how you would say that. It's the power series representation of the function that we get after we integrate twice, right? We integrated 2 times and we got this function. And we found a power series for that, okay? Well, shouldn't it make sense then if I take 2 derivatives of this function, in fact, if I differentiate both sides of this 2 times, right? So take 2 derivatives of both sides. Okay, so let's see. Derivative of 1 over 1 plus x must be equal to the derivative of the other side, right? Because we're just differentiating both sides. And then here we have to think about how we differentiate a power series. Well, like I said, they're just polynomials, so they're very easy to differentiate. The right side is going to give me, power rule says what? Put the n in front, lower it by 1. That's all you got to do. So put the n in front, lower it by 1. And if I differentiate the other side, that's just going to give me negative 1 over 1 plus x squared, right? I mean, we already knew that because we took the integral already anyway. Now remember what we said about differentiating, taking a derivative of a power series. The first term is actually a constant here. If you see, if you plug in 0 here, you're going to get x to the 0 power, negative 1 to the 0 power. The first term on that is just 1. When you take that derivative, that 1 is going to drop off. And so we have to increase this by 1, okay? And we would also like to keep it so that it does have a 0 index. So I'm going to change it back to 0. And the way that you do that, again, is by, if you lower the index by 1, then all other occurrences of the n must be increased by 1. All right, so now what I have is the power series representation for the first derivative of that function. Let's differentiate it one more time. And keeping in mind what this represented, this power series was the first integral of the original function. Now if I differentiate again, the left side should take me back to the original function, and indeed it does. 1 over x, or 2, sorry, 2 over x plus 1 to the third, or 1 plus x to the third. Now remember, that's the same function that we started with, right? And then if I differentiate this power series, again, notice that the first term in this case is still a constant. So I have to increase that index by 1. Take the derivative, I'm going to get n plus 1, x to the n minus 1. And then if I want to change that index back to 0, I can. Okay, then that's going to increase by 1, n plus 1, and that's going to increase by 1, so that will give me n plus 2, and then I'll get x to the n. I'm just going to leave that as an n. Technically speaking, when I dropped that by 1, this had to increase by 1 also, but that really became n plus 2. But if you think about it, n plus 2, when I have negative 1 to the n versus negative 1 to the n plus 2, that's the same thing, right? And so I can change n plus 2 back to n there. What I have here, what is this? Well, according to what I have on the other side, this thing is the answer to the question. That is the power series representation of the function 2 over 1 plus x to the third. Okay? And this is only going to work again for x less than 1. What did we do? Just to review, we wanted to find a power series representation for this 1 over, going way back up here, 2 over x plus 1 to the third power, right? And in order to do that, well, what did we have to do? We had to integrate the function 2 times. Integrating twice brought us to this point where we can now finally use this formula here, okay? And then we wrote the power series for that, right? So that's this step right here. We wrote the power series for that. And then we realized, okay, well, if I want to get back to where I was before, what do I have to do? Well, since I integrated 2 times to get to this point, how do I get back? I have to differentiate 2 times to get back, you see? And so once I reach this point here that's circled in red, to get back to the function that I started with, I had to differentiate once and then twice, and that got me to here, the original function that I started with. But then what else did I do? I also differentiated the power series once and then twice and simplified it and got to the final answer there. Okay, so it's a very roundabout way to do this, but it's actually pretty clever. If you want to find a power series expansion for certain functions, this is a pretty clever way to do it. All right, that next example, arctan 2x, if you think about that. So B, again, the goal is to find a power series representation for arctan 2x. And again, if you think about it, we're still using that same one. We want to use this 1 over 1 plus x equals negative 1 to the n, x to the n. And again, that only works for x less than 1, absolute value x less than 1. But this looks nothing like that, right? I mean, this doesn't look anything like 1 over 1 plus x, okay? But if you think about it, its derivative does. The derivative does. So thinking about the derivative of arctan, and again, think just the formula for the derivative of arctan. Remember that? Remember what that is? That's u prime over 1 plus u. Okay, so on this problem, then u is 2x. So u prime is going to be 2, and then over 1 plus u squared, so 2x quantity squared. So this is the same as 2 over 1 plus 4x squared. Well, this is already, I mean, this one actually is slightly easier than the one we just did because we only had to take one derivative, and we're already in the place where we can go ahead and actually use that. So this x here, right, it's got a 1 which it needs to, it's got a plus which it needs. So really the only thing we're going to do then is just replace the x here and here with this. Okay, so we can just immediately jump to the power series now and say this must be the same as the power series for 2 times negative 1 to the n times 4x squared. And you can simplify this a little bit if you want to. This is the same as 2 times negative 1 to the n times, now that 2, again, just to kind of, this is not 100% necessary, but just to show you how to make these look a little bit nicer. 4 is the same as 2 squared, and so you have 2 squared to the n there. And then you also have x to the 2n. And I'll just do one more simplification step here. And then notice this is the same as 2 to the power of 2n, and then I have this other 2 there, so that becomes 2 to the power of 2n plus 1. Okay, so what we end up with here is negative 1 to the n times 2 to the power of 2n plus 1 times x to the power of 2n. And this will converge for 4x squared less than 1, or x squared less than 1/4, or x less than 1/2. So the radius of convergence for this thing is only 1/2. Now, again, keeping in mind that this was the power series for the derivative, right? This is the power series for 2 over 1 plus 4x squared. Now, if I take the antiderivative of both sides of this, then I should get back to arctan 2x, right? So arctan 2x then must be equal to the integral of this power series. Okay, and then we have to put a dx on the end. This is an integral, regular old integral. Anyway, the integral is just as easy as the derivative. It's just a power rule for integration now. What does the power rule for integration say? All of this other stuff is just constants. What do you do when you integrate a power function? You just raise the power by 1, right? But then you also have to divide by that same power, so we put the 2n plus 1 down there. And then you put a plus c on the end as well, because it is an integral, right? Now we can actually figure out what that c is, because notice arctan 2 times 0, in other words, if I plug in 0 here, must be equal to the same thing that I get over here when I plug in 0, plugging in 0 here. But if I plug in 0 there, what is that going to do? That's just going to make the whole thing 0, right? and then I'll have the plus c there. So it turns out that the c value is in fact the output of the center when you plug the center into the function itself. Well, what is the arctangent of 0? It's just 0. So this is just 0. So c, in fact, is 0 here. And so what is our final answer here? What is the power series representation for arctan 2x? Well, it must be this. And if you notice, when I took an integral of this thing, I didn't have to bother with changing that index. That's kind of nice, because when it was derivatives, what happened was that that term disappears when you take a derivative. Well, terms don't disappear when you take antiderivatives, right? In fact, terms appear when you take the antiderivative. The plus c appears, it doesn't disappear. So we don't have to bother with changing the index in this case. Okay, and then it also turns out that the interval of convergence doesn't change either from the original function, so still is less than 1/2. So there we go. This is our answer. The power series representation of arctan 2x and the interval for which it converges, or at least the radius of convergence anyway. Let's go ahead and continue with example 3. All right, so this one says to find a power series representation of the function and determine the interval of convergence. Okay, so here's the function. And again, for these types of problems, we use that one power series. 1 over 1 plus x is equal to this particular power series. Okay, so we just have, if we remember from last time, we need to put this thing into that same form, although we have this x squared in the numerator. The way we deal with that is we just write it off to the side. So we get x squared times this. Okay, and then we need to take care of that 16 right there. Remember that we need that to be a 1. So we make that happen by factoring out that 16. So we'll take the 16 out of the denominator, leaving us with 1 plus x to the 4th over 16. And then you can write that 1 over 16. You can move that to the numerator if you want to, just to realize that that's the a value. If you have an a there, then that just gets multiplied by the power series. So we'll have 1 over 16. Okay, and then that's in the form that we need it to be, so we can put this as x squared. We can put the 1/16 out in front as well. And remember that the way this works is you put, since this has a plus, you put the -1 to the n, and then whatever is right here, whatever is right there, takes the place of the x in that formula there. So that means we'll put x to the 4th over 16 there. So the way that we deal with this other x squared out here, just realize that what that actually is you have like x squared multiplied by, remember what that is just overall, what is that thing? That's a polynomial, right? So if you were to write it out longhand, you would get like, and I guess we could put the 1/16 there as well. What happens when n is 0? You'd get just 1, and then the next term would be, if n is 1, so you'd have minus x to the 4th over 16, yeah, x to the 4th over 16, etc., right? And so you have all these terms here, but it's all just polynomials, right? So what I'm doing again is I'm writing out the sum sort of longhand, right? That's what this is. That's the sum. Now just remember what you can do when you have a monomial like this multiplied by a polynomial, right? What can you do? You can just distribute it in there, right? Well, this is just going to get distributed to how many terms? Well, infinitely many terms. But it can get distributed nonetheless. So all we really have to do here is just combine that x squared with this x that's already here. Okay, so that's what this is what that would look like. Let me clean this up and show you what all that would look like. It's actually pretty simple to deal with that x squared term. You just have to combine it with the other x's that are already in there. So I'm going to go ahead and move everything inside the sum now, including the 1 over 16. And I'm going to rewrite this. I'll put the x squared inside there as well, and I'll go ahead and simplify that. The stuff that's in the parentheses there, that's going to be x to the 4n over 16 to the n. Okay, now again, the idea here is both of these are x's. What do we do when we have base x raised to 2 different powers? You multiply them together, you add the exponents, right? So then what we can do there is just write this as, I'm going to go ahead and put some stuff in the numerator here, so we'll have -1 to the n we've got x to the power of 4n plus 2, and then the denominator, you see we have a 16 here, and we've got a 16 to the n there. Those can be combined and called 16 to the n plus 1. Okay, so there it is. And then they also want us to find the interval of convergence on this thing. So the way that that works, again, is once you have the thing in this particular form, that you can use this, and we reach that step right here. Just remember that the thing that needs to be less than 1, right, I guess I should say up here, this is only valid, of course, provided that absolute value of x is less than 1, right? And so what we do on this case is we just look at what is here, and that is the quantity that has to be less than 1. So that's the way we find the interval of convergence for these. So we want x to the 4th over 16 absolute value to be less than 1. And so you can solve that. X to the 4th less than 16. 4th root of 16 is 2, so we get x less than 2. Okay, and again, I'm not just ignoring the absolute value bars. Remember that when you have a 4th power, you don't need them. But then when you take a 4th root, you have to put them back. Okay. All right, so that means that our radius of convergence is 2. And you can see where this thing is centered, again, just by looking at the power series itself, particularly that that's just an x. It's not like x minus 1 or x minus something else. It's just an x. That tells us that it's centered at 0. And so to find the interval of convergence, I know that the thing is centered at 0. I can just set this up as a compound inequality, which looks like this, and there's your interval of convergence, -2 to 2. Or if you want to write it as interval notation, you could write it like this, -2 to 2. Okay, and remember what I said about endpoint checks here, right? We're not using the ratio test here. How are we determining this interval of convergence here? We're using the fact that on a geometric series, a geometric power series, or any geometric series, that this is already set, right? This quantity here is already set. There's no possibility of that being equal, and we know that because this is a geometric series. So there's no reason to check the endpoints because we know it's not going to converge at the endpoints because this is coming from a geometric series. So again, this is how you deal with problems that have somewhat of the form of that geometric power series, but then you have like an other x's in the numerator as well. How do you deal with that x stuff in the numerator? It's just a monomial. You just combine it with the other x's that are in the power series, okay, using the properties of exponents. All right, another thing that we are able to do with power series is we're able to find antiderivatives of functions that we wouldn't otherwise be able to, okay? So power series give us a cool way of finding antiderivatives. So take a look at example 4. The goal here is to figure out what is an antiderivative for this function t over 1 minus t the 8th power. Now, if you think about that integral just in general, thinking about back to the techniques of integration that we've seen, I wouldn't even know which one to try here. It's really, I'm not even sure that we could find an antiderivative for this using any of those techniques. So chances are we wouldn't be able to. However, we can do it with power series. So this is how that works. So first we would like to find a power series representation for the integrand itself, the t over 1 minus t to the 8th. So that's our goal first. And again, remember that this is pretty much the same as the last example. We have that monomial in the numerator, and in the denominator is that 1 minus something, and that is already ready to go for the geometric power series. So we just rewrite this like this, look at the term in parentheses and say, okay, that's already exactly what we want it to be. It's got the minus sign there, it's got the 1 there. We don't even have to do anything to make this ready for a geometric power series. So we can just immediately turn it into that. And then this has a minus on it, so it doesn't even need to have that -1 to the n. All we have to put here is simply t to the 8th. And then we can simplify that. Now that's actually t to the 8n, and then there's that other t out there in the front, and remember how we deal with that. We just combine it with the other t. We get t to the 8n plus 1. Now the interval of convergence here is not going to change. So this thing is going to converge. Again, what we look for is what is the quantity that's right here, or if you want to, just the quantity that's right there. Whatever that quantity is, that's what needs to be less than 1. And so we know that in this case, we want t to the 8th to be less than 1. And if you solve that inequality, you just take the 8th root. Well, that's just going to give you t, but really absolute value t. And so that's the radius of convergence right there. And that's not going to change as far as what we do after this. Okay? Okay, so far what we have is the power series representation for the integrand. So what we want though is the integral in total. So we want to have to, or we have to change this into its power series representation, which we just found was this. So t to the 8th, t to the 8n plus 1. And we're going to integrate that now. And so remember with power series, we just have to use the power rule because these are fundamentally just a bunch of power functions added together. And so the antiderivative here is simply what we get when we add 1 to that exponent, right? So 8n plus 2, and then we're going to have to divide by that same thing that we just raised it to, right? That's what the power rule for integration says. And then we have a plus c on the end of this. Okay, so now in this case, the plus, we can't figure out what that c is because this is just a general antiderivative, okay? If you remember in that previous problem, the arctan one, we could find c because we weren't trying to find the antiderivative of arctan. We were just trying to find arctan itself, or arctan 2x. So we weren't asked to find an antiderivative. Here we are. And so since we have an antiderivative in general, any antiderivative, even power series ones, you have to have that constant of integration, and that's what that is here as well. Okay? Okay, and then the interval of convergence, or sorry, the radius of convergence just stays the same. So we can just say this is going to be valid for only for t, absolute value t less than 1. All right, so there's the answer. That is the antiderivative. And you can see that's actually not, I mean, if you look at the steps we did here, it's really not that bad. It wasn't that much work to find this particular antiderivative. If you, again, if you were to try to do this by those elementary methods that we had seen earlier in the semester, I doubt any of them would actually work. So again, this is probably an integral that can only be done by power series, or an antiderivative that we can find only by the method of power series. All right, so there's a couple of problems that I want you to try here. Problem 1 is pretty straightforward. Just find the power series. You just remember you have to make it so that it fits that correct form. That one's already almost there. It's got the 1 there in the place that it needs to be. You might have to factor a -1 out, but that's okay. And then the problem 2, I haven't actually done anything like that before, but I do give you a way to do it. And so what you're going to do on this one, that it says right there, first use partial fractions. Okay, so that's your first step. This is problem 2 that I'm looking at on the worksheet, okay? Do the partial fraction decomposition on that, and when you do that, what you're going to find is you're going to have two different functions that both look like, you know, the 1 over 1 minus x, or 1 over 1 plus x. And then you can use those special power series that we've been doing in this whole section, right? Change those into power series, but you're going to have two of them. You're going to have to change them both into power series, and then you basically just have two power series added together, which is perfectly fine. So that's the way that you deal with that. And then for the interval of convergence, I want you to think about, like, you're going to have to check the interval for both of them. So think about how you're going to get the one you actually want, right? Because they both have different intervals of convergence. Which one do you want to pick? Or is there some way to figure out what the interval is supposed to be? And then on problem 3, if you can figure that out, that would be great. It is a tricky one. Okay, let's take a look at these problems.
This one's actually got a lot of unnecessary work now that I'm thinking about it the way that you're thinking about it.
Yeah, I was going to point that out, actually. I mean, all of this is totally correct up to, I mean, it's all correct. But right here, looks like you're trying to do the ratio test to determine convergence. But yeah, this is not nothing below that line is necessary here. The only thing you really need is just, you can make that conclusion just based on the fact that we're using the geometric power series here. Okay, so everybody see kind of what the procedure is. You first want to put this exactly in the correct form, and that is to have just a 1 right here. And since it starts out as a -1, you have to factor out the negative. So that's what he's doing in that step there, factoring out the negative. then you can put that negative up there on the top and just make that the a value, the negative value there. And then once it's in that form, really you can just jump right to here and say, okay, put the -3 in front, plug in the 2x where the x would normally be, and then that's it. And then if you want to, you could even rewrite it as -3 times 2 to the n x to the n. Okay, and then again, just based on the fact that this is a geometric power series, you can take that 2x, and that is the quantity right there that needs to be less than 1. Okay, and then just solve that. This is the radius of convergence here. And again, because this is a geometric series, we know that there's no chance of convergence on the endpoints, so we don't ever even have to check that. So yeah, the stuff below here is not necessary. You don't have to actually check the endpoints. We know what's going to happen there. They are definitely going to diverge. Again, because of the fact that this is coming from a geometric series, and we already know what the conditions are for convergence of a geometric series. Okay, so any questions on this one? All right, then number 2, I'll just go down here. This is the one I was saying, do the partial fraction decomposition first. So that's what is going on here. I hope everybody's cool or okay with partial fraction decomposition at this point. When you do that partial fraction decomposition, you get this. I guess both of them are equal to 1. And then you would then do two different power series, one for each of those. And similar to the last one, remember you have to have it in that proper form. It has to be 1 minus x or 1 plus x. And since this is a -1 right here, you have to factor out a negative. And so that's what he's doing, factoring out the negative, putting it in the proper form. And then in the second one, there's a 3 there. You have to get rid of that 3. In fact, it's a -3, so you need to make it positive and you need to get rid of the 3. So he's factoring out a -3 there. And then just, yeah, I guess this is just a simplification step right here. And then that first power series, this one here, there's the negative in front, it just stays there. The rest of it, that is the geometric power series right there, right? It's just an x. It's already set up perfectly for it. So there it is. The second one also has a negative, and you got the 1/3 as well. And so you get that, and then again, in this case, what gets replaced with what replaces the x? The x over 3 does. Okay? And then the rest of this just seems to be cleaning stuff up, right? That's what you're doing to get to here, I guess.
Yeah.
Putting them as a single power series. Although even that is not 100% necessary. This would be a perfectly acceptable answer. Although I'm not sure on WebAssign if they want it as a single power series or 2 power series. If they want it as a single power series, then yeah, you would definitely have to go on and put it into this form right here. But that's just finding a common denominator, adding stuff together. That's what he's doing in those steps to get to that point right there. Again, the ratio test is not necessary here because we know what conditions for convergence are. So all we really need to do is just look at this here and then this here. Those two things are going to tell us what the radii of convergence are, I guess. This one here is going to tell us that it needs to have this true for convergence, and this one is telling us that we need to have this true for convergence. Okay? The first one just has a radius of convergence of 1. The second one, you can solve it and get a radius of convergence of 3. So this first one is telling us that the interval of convergence, since it's centered around 0, would be -1 to 1. The second one would be telling us that the interval of convergence is -3 to 3. Now, what I was trying to go for here to get you guys to think about is which one of those would be the one that would satisfy both of those parts of that power series. Well, since one of them is not going to converge any farther away than -1 to the left and +1 to the right, we know that this one here, the first one, the x to the n one, this one right here, is not going to converge farther away than 1. The second one, this one here, will converge farther away than 1, but we're looking at both of them as a single series, so we have to take the smaller of the two. And so the actual interval of convergence here has to be this one right here. It's got to be -1 to 1. Okay, so when you're faced with this kind of thing, you have to do a partial fraction decomposition on it. What's the radius? And then there's two different series that you're checking. which one do you want to choose? You always want to choose this one that has the smaller interval, okay? And if you look at both of the intervals together, that would be called the intersection of the two intervals, the overlap, basically. Like if you were to graph one on top of the other, the -3 to 3 one would be, out here. The -1 to 1 one would be here. Where do they overlap? They only overlap on the -1 to 1. Okay? So again, this rest of this stuff here, you do not need to do the ratio test on these. It's already determined by the fact that this is a geometric power series, so no need to check those endpoints or even do any of the ratio test stuff at all. Okay, then last problem. So Michael, I was just looking at what you were doing here, and it seems that you might have been using the table to get this. Is that right?
Yeah, I used a table for that, and then there's an error at the bottom when I was dealing with the constant of integration.
Okay, so actually I'm going to go through this problem separately because that's not the method that I want to show them here.
Oh, okay.
Because we haven't reached the table yet. That's in the next section. So we have to do this with methods that we've seen in this section. So I'm going to go ahead and redo problem 3 here to show you the way that it needs to be done, at least with methods of section 11.9. I mean, it's perfectly fine. It definitely is a correct answer. It's just not the method that we need to be doing in this particular section. Okay, so I'm going to redo that one. This is number 3. Okay, so again, if you kind of just look at that thing, thinking about methods you might want to try this for with stuff we've seen previously in the semester, I would say maybe integration by parts, but I seriously doubt that would even work. So it's probably not even doable by any methods that we've seen previously, although it could be. I don't know. I haven't tried it. But anyway, the point here is we want to do this as a power series integral. So this is the way that we approach that. We first want to figure out how to do the power series for ln 1 plus x. So that's this first step here. First find power series for ln 1 plus x squared. Okay, how do we do that? Well, we have to notice that its derivative is this. It's 2x. Remember your chain rule there, 2x over 1 plus x squared. And now that can be certainly written as a power series. So what we can do there is write that as 2x times 1 over 1 plus x squared, and then just realize that could then be written as this power series. Since it's got that plus in between, we do have to put the -1 to the n on there, and then we'll have x squared to the n on that. And then this would converge for x squared less than 1, or just x less than 1. Okay, so radius of convergence there is only 1. And then we can clean that up a little bit. We can write this as -1 to the n. And then we've got the x to the 2n. And then we also have that other x that's floating out here. And so remember how that works. This is x to the 2n. This is x to the first. You're multiplying them, so it becomes x to the 2n plus 1. Okay, so now remember that this is the power series for the derivative of this ln 1 plus x, right? And so that means that the antiderivative of this, ln 1 plus x squared, remember, you see what I started with, right? I took the derivative of that. This is the derivative, and that's what we found the power series for, okay? So I want to take this backwards now and find the antiderivative to find the power series for the ln 1 plus x squared. So this then must be the antiderivative of the power series we just found. All right, so now we want to integrate this. Okay, so now we're just going to use the power rule for integration. The power rule for integration says we just have to add 1 to that thing. So we get 2. All of this other stuff is just coefficients. Those don't change. The only thing that changes is the exponent on the power on the x, and we're going to also be dividing by whatever it is we raise that to. So we have to raise this by 1 to the 2n plus 2 power. Then we also have to divide by that same thing that we raised it to. And then we have our plus c on the end of this. And remember that c is equal to f of the center of the power series. And in this case, well, I'll just write it as f of the center. But in this case, that's the center of this power series is 0. And so we come back up and look at what was f of 0. Well, if I plug 0 into that function there for x, you get ln 1, right? Well, ln 1 is in fact 0, and so c is equal to 0 here. So that means this power series, we can just drop that c off of there. And then also further notice that you can take a 2 out of the denominator here. You can factor a 2 out of the denominator, and then it'll cancel with that 2 in the numerator. So we can at least do a little simplification step on this and say this is equal to -1 to the n, x to the 2n plus 2 over n plus 1. Okay, so everybody understand where we are right now. What did we just do? What is this thing? What is this power series right here? What does it represent? Well, if we follow our equal signs back, right? Equal, equal, where did we come from? We came from here, right? And so that means this is the power series for ln 1 plus x squared, okay? So you see how we got that, right? How did we find the power series for ln 1 plus x squared? We took its derivative, we found the power series for that. And then we took that power series and we integrated it, which took us back to ln 1 plus x squared. Now we have a power series representation for ln 1 plus x squared. Well, what am I really after, though? At this point, what I'm trying to find is a power series representation for the integrand of this thing. And right now I've got that. I've got a power series representation for that. So I need to find the power series representation for that times x squared, though. Right? And then I can find finally, the last step would be to find the antiderivative of that. And so our next step is to find the power series representation for x squared times ln 1 plus x squared. Okay, so again, just keeping in mind, this represents ln 1 plus x squared. Now, one other thing here, this problem is only asking for the radius of convergence, which is good. I don't think I mentioned this last time, but when you integrate a power series like this step that we just did here, integration step, right? What happened when we took that integral? We introduced a term in the denominator, right? And then simplified it, became that. If you think about it, that power series, just look at it, that one actually will converge at one of the endpoints. In fact, it'll converge at both. If I plug in 1 there, see what happens? Like if I take that 1 and plug it in here, what do I get? Well, that x term is just going to go away, right? Because 1 to the 2n plus 2 is just 1. And then if you look at the power series that remains, it's just going to be this, right? Well, that actually will converge. You would use the alternating series test and show that it would in fact converge. And so what actually ends up happening here is that this thing does end up converging at the endpoints. And so really, in that case, you could put the equality on there, okay? So we got this from a geometric power series, but we ended up integrating that power series. And that act of integrating it, that step of actually doing that integration, it caused the endpoints to be included all of a sudden, where they weren't before. Now I'm not going to, and again, this problem is only asking for the radius of convergence, right? It's not asking for the interval. And the radius of convergence, we don't care about the endpoints on that. And so in this case, it really doesn't matter for the purpose of this problem. I'm just kind of pointing it out here that when you integrate a power series, especially if that power series came from a geometric power series, where the endpoints definitely weren't included, the act of integrating it itself can potentially make those endpoints become included where they weren't before. It will never happen with a derivative, though, only with an antiderivative. So I hope I'm not confusing things more than they need to be. But anyway, what we're after here is this. We need to find the power series for this now, right? Because that is the integrand of the integral we're trying to find for the whole problem. Okay, well, again, those aren't that hard to find because as long as we've got the power series for the ln 1 plus x squared, it's pretty simple to just do that multiplication with a monomial times power series. Remember, you just add the exponents. So now I'm going to combine that second power with these up here. And again, that's not too bad to do. You just add them, right? So it's just going to become 2n plus 4 now. All right, so now what we finally have here is a power series representation of the integrand, okay? So now our last step here is now I actually want to integrate that. So I've got a power series representation for x squared ln 1 plus x squared now, okay? And now my final step here is just to change that x squared ln 1 plus x squared into its power series representation and then integrate it. And now again, that just requires the power rule. So I'm going to get my final answer here as x to the 2n, this gets raised by 1, so x to the 2n plus 5 And we have to divide by that as well, so we're going to get n plus 1, 2n plus 5 in the denominator. And this is a genuine antiderivative here, so we have to put the plus c on that, but there's no way we're going to find what that c is because, again, this is just find a general antiderivative, and so we've done that. All right, so here it is, and then the radius of convergence is just 1. That doesn't change. The radius of convergence doesn't change. The interval of convergence, in fact, it would actually end up converging on both endpoints, but that's not what was asked, so we don't care about that. So again, just to kind of, if you want to think of this in the overall sense here, what did we just do? We started out with this function here, x squared ln 1 plus x squared. You know, that function would have a graph associated with it. And what we just did is we found an antiderivative for that. So if we were to actually graph this function here, this power series, what we would find is that its derivative would match that function we started with, right? The derivative of this power series would actually be x squared ln 1 plus x squared, of course, only from -1 to 1.